Hello everyone, welcome back to the lecture series of satellite communication and networking. In the last session we have started our unit 8, that is the space link, right? And in that session we have discussed the basic transmission theory and about the system noise temperature, right? Now in today's session we are going to discuss various topics such as introduction, then basic terminology related to space link, then noise figure, noise temperature, and last that is the losses in the space link. So let's start one by one with this topic. Now first, that is the introduction. So what does the space link consist of? So as we have discussed in the last lecture, so basically the space link means that is the two links which are created during satellite communication. First, that is the uplink, and second, that is the down, right? So in this link budget we are calculating ultimately that is the received power when we received a signal after transforming this through the satellite, right? So those are the transmitting and the receiving power calculations. The space link is nothing but that is the calculation of receiving power. In satellite communication system there are two types of power communications, and these calculations, they are called as a link budget calculation, and always we will calculate the received power in terms of this decibels, right? Now what are the different basic terminologies related to this satellite communication or the space link? So first, that is an isotropic radiator antenna radiates equally in all directions. It doesn't exist practically. So as I have said already in the last session that that in the basic terminology we are talking about the isotropic source, but in the practical sense isotropic source doesn't exist, and we have the antenna which is called as a radiating, or you can say directional antenna, in which the direction of antenna for transmitting as well as receiving purposes is defined, right? Now, so it is just a theoretical antenna. We can compare the performance of all real antennas with the respect to this antenna, right? Now first, that is the basic terminology. First, that is the power flux density. So in this we have already discussed the in basic basic transmission theory about the flux density. So flux density, that is nothing but the power divided by its area, right? So assuming an isotropic radiator is situated at the center of the sphere wherein radius r. So the power density is defined as the powers of the source, radiated source, divided by the total area which is covered, is called as a power flux density. Now, so the definition of flux density, which is denoted by psi I, so that is called as psi I is equal to PS, that is the power from the radiated source, divided by the area. Here we have taken a circular surface, so the area will be 4 pi r square. So where PS is the power flow, in general the power flux density of a practical antenna varies with direction, but its maximum value will be in one particular direction only. Now second terminology, that is the antenna gain. So already we have discussed that there is a no isotropic source, and so the antenna which we are using in the satellite communication practically, that is the directional antenna. So each and every directional antenna has its own gain. Gain suggests that in which direction the maximum radiation will occur, right? So the gain of practical antenna is defined as the ratio of power flux density of the practical antenna and power flux density with respect to isotropic antenna. So the gain is defined as denoted by capital G, and capital G, that is equal to psi m divided by psi I, where psi m is the gain of the practical antenna and psi I is the gain of the power flux density of the isotropic radiator or antenna. Clear? The third terminology, that is the EIRP, which stands for equivalent isotropic radiated power or effective isotropic radiated power. So EIRP is the main parameter that is used in the measurement of the link budget. So mathematically it is represented as EIRP, that is the product of power and gain. So EIRP, that is equal to G into PS. But when we represent this EIRP in terms of decibel, so as we have discussed in this introduction slide, that in this space link whole chapter we will describe the power in the decibels. So when we convert this value into decibels, for converting this decibel we need to take log 10 log on both the sides. So EIRP in the square bracket, the square bracket always denotes that the value is suggested in the decibel. So EIRP, that is equal to G, and the multiplication in the decibel will convert it into addition. So EIRP plus G, EIRP is equal to G plus PS, and the unit will be dB watt, that is decibel watt, where G is the gain of transmitting antenna and PS, that is the power of the transmitter. Now, transmission losses. So, as we have discussed that whenever the earth station is transmitted any signal, that is received by the satellite, and whenever the opposite occurs in the downline, so again there is a transmission process. So during transmission, as we have suggested that the satellite communication occurs in the free space transmission. So in the free space transmission, various transmission losses occurs. So that the transmission, the difference between the transmission power and the received power, that is called as loss. So here the loss is calculated or categorized into two types. First, that is the constant loss, and second, that is the variable loss. Now, the losses which are constant, such as feeder loss, are known as constant loss. That means any antenna is connected with the help of cables, filters, right, couplers, right, and various blocks of the transmitter antenna. So each and every type, whenever there will be a transmission, there will be a feeder loss due to this cable. So that is the constant for all the particular antenna. So no matter what precaution we might take, still these losses will occur. So as it is a conduction, as it is a conductor, so the conduction loss of this type will occur, which is called as feeder loss. Now, another type of loss is a variable loss. The sky and weather condition is an example of the type of loss. Means if the sky is not clear, as a clear signal will not effectively to the satellite or vice versa. That means when we talk about the atmospheric loss, or you can say about the weather conditions, that type of losses is a variable loss, because it depends on the type of weather. If it is a clear, then the signal will pass easily with the help of some loss occurs between them. But if the signal is not, if the atmosphere is not clear, there are clouds in between them, so, or if the rain is falling right now, so at that particular time the signal will have the loss, or different types of loss occurs in this process, right? Therefore, our procedure includes the calculation of losses due to clear weather or clear sky condition as first. So, therefore, our procedure includes the calculation of losses due to clear weather or clear sky condition as first, because the losses are constant. They will not change with the time. Then in the second step, we can calculate the losses due to the foul weather conditions, right? So basically, when we talk about the transmission loss, which we will discuss in detail in the next slides, right? So what are the different losses occur in the satellite system, right? So here we have categorized these losses into the two types, that is the constant loss and the variable loss, right? Constant loss comes under the feeder loss, where it is a constant for each and every antenna. When and variable loss comes under this weather condition losses, where it depends on the types of weather which is occurring right now. Right now, next term, that is the noise figure and noise temperature. So what is this, a noise temperature, and what is the noise figure? So first of all, noise figure is used to specify noise generated in the system. So the noise figure is defined by signal to noise ratio at the input divided by signal to noise ratio at the output. Now, what is basically signal to noise ratio? So it is the ratio of signal power divided by noise power. So whenever we talk about any device in the communication system, it depends on the signal to noise. There is some signal to noise ratio of each and every communication block, right? So whenever the signal or input power is transmitted, right, there is some type of loss occur in this communication system, and the ratio of the signal power to the noise power, that is called as a signal to noise ratio. So when we talk about the signal to noise ratio at the input side and at the output side, and when we take the ratio of both this, then it is called as noise figure, right? And if we calculate this noise figure in terms of decibels, then it is called as noise factor. Clear? Now, next, that is the noise temperature. So noise temperature is more useful in satellite communication system. It is the best to convert noise figure to noise temperature. With given equation T is equal to T0 into bracket NF minus 1, where NF stands for the noise figure, and T0, that is the ambient, or you can say room temperature, which is absolute, taken as 290 Kelvin. Clear? So based on these equations and the equations we have studied in the last session, they related to freeze transmission equations, we will see different types of example in the next session. Right now, next, that is the what are the different losses in the space link. So when we talk about the uplink or downlink side, let's talk about the uplink side. So what will happen? It will have a transmitting antenna, or you can say earth station, and at the receiver side there will be a receiving antenna. So in between transmitting and receiving, there will be a link occur which is called as free space transmission. Right now, during this free space transmission, as we have discussed in the basic transmission theory, that one type of loss occurred with the distance, which is called as path loss. Right now, whenever the signal transmits, right, again we have discussed in the transmission loss that one type of loss which is a constant loss which occurs every time, that is called as feeder loss. So feeder loss will occur, then path loss will occur. Then whenever the signal will transmit in the free space, there will be a different layers of atmosphere. So atmospheric loss will occur. When it will happen, it will go into ionosphere layer, then the polarization loss will happen. And if the transmitting antenna and receiving antenna, if they are not aligned properly, then antenna misalignment loss will happen. Right? So these are the different losses which occurs in the space link. Right? So let's discuss one by one. Now first, that is the free space path loss, which is denoted by LP. So in the last session, we have derived the equation which is freeze transmission equation based on the path loss. Right? So in that we have discussed the denomination term in the freeze transmission, that is 4 pi r divided by lambda whole square. So that is called as the path loss. Right? So the path loss is a loss occurred by an electromagnetic wave as it propagates in a straight line through a vacuum with no absorption or reflection of energy from nearby objects. Right? And LP is independent, frequency dependent, and it will increase with respect to distance r. As it is directly proportional with r, so it will increase as the frequency also increase and as the radius also increase. So as you can see the below in the slide, that LP is given by 4 pi r by lambda square, and if we replace the lambda with c by f, then the equation will be 4 pi f r divided by c whole square, where c is the velocity of light. So this is the first loss occurred during this space length. Right now, second, that is the when it travels in the atmosphere, that is the atmospheric loss, and when it enters into the ionosphere, that is the ionospheric loss. So it is denoted by Lu and Ld. So atmospheric losses occurs with the help of atmospheric gases. So atmospheric gas results in the loss by absorption. These losses usually amount to a fraction of dB, and it is denoted by AA. So AA denotes the atmospheric loss in the space length. Right now, similarly, when the signal enters into the ionospheric layer during that particular time, the polarization of signal changes. So with the help of this ionospheric, there will be a polarization loss which is denoted by PL. Right? So two losses again, that is atmospheric losses and the PL, that is the polarization loss, occurs in the ionosphere. Then next, that is the feeder and branching loss, which is the constant loss. Right? So each and every antenna which is transmitting will be connected with the help of cables, filters, couplers, which is the conducting device. So each and every conducting device will have a type of loss which is called as feeder or branching loss. So losses will occur in the connection between the waveguides, filters, couplers, and branching units. So losses due to this, that is called as the feeder loss, which we will also calculate during this freeze transmission, or you can say power received calculations. Then fourth, that is antenna misalignment loss, which is denoted by AML. So as we have discussed that AML occurs, that this antenna misalignment loss. So whenever there is a transmitting and receiving antenna, and if they are not pointing properly to the each direction, then there will be an antenna misalignment loss, and that is called as antenna pointing loss. So losses that occurs as a result of earth station and satellite antennas being off axis, means their axis doesn't match. For ES, these losses is called as antenna pointing loss. And last, that is the polarization misalignment loss, that is the PL. So losses occur during the polarization, that is called as polarization misalignment. Clear? So these are the various losses which occurs in the space link. So whenever we will calculate the received power, right, at the satellite side for the uplink process, we will calculate all these losses taken, we will take into a consideration, as well as we will take the power and the gain of the transmitting antenna as well as receiving antenna, right? So we will derive the equation, the Friis transmission equation, for again for the uplink as well as downlink, while taking this type of losses occurs into the consideration, right? Now here you can see the figure in which AML, that is antenna misalignment loss, is defined. So here you can see that in the first figure, the transmitting antenna as well as the receiving antenna both are pointing, and both the axis of these antenna match with each other. So there is no misalignment loss in this type of figure. But when you compare this second figure, you can see this transmitting and receiving antenna have different axes, right? So as the axes are different, there will be a some loss due to this antenna pointing loss, which is called as antenna misalignment, right? So here these are the various types of losses when any space link occurs between either uplink or downlink process. So that's all for today's session. In this session, we have discussed about the various types of losses, as well as noise figure and noise temperature, and the basic terminology related to the space line. Right now, in the next session, we are going to discuss the examples related to this Friis transmission, as well as the examples related to this losses which we have discussed in this space line. Right. So that's all for today's session. Thank you for watching.